Hello, we're back again. We're gonna continue recording this set of videos in order to help all of you follow this subject from your houses due to this strange period of self-isolation. Okay, today we're gonna focus in the first shock we find when we start working with financial issues and arithmetics and geometric compounding and so on. So there will be no theory about that, but just remind all the previous knowledge we all have from our traditional standard, uh, let's say, arithmetic knowledge from the high school that we take into account and we collect in order to have basic instruments for working in this subject. Okay, so let's go for it. Okay, the initial problem we're going to focus is quite simple. Look at this. The inflating price of gasoline. The average price of gasoline in 1 year was $2.3 per gallon. In 1993, that is 12 years before, the price was 107. So what's the average annual rate of increase in the price of gasoline? Okay, what do we know from that? The arithmetic is quite simple, but let's dedicate a couple of minutes to it. We have an initial price, P1, at moment 1993. Let's call it P1993. We know this. And this price is subject to a rate, a given rate of an unknown rate of growth. We call this G. Sorry. So this price is transformed into, G, into every year into an increase. The initial value plus a proportional growth rate. Let's say 3%. Okay, the price at the following year, 1994, will be the price initial times 1 plus 3%, 4%. Okay, so this growth will keep on existing until we reach the final point in the final year in 2005. So if this is the case, the process will repeat during 12 years. Actually, we could be saying this. The first year, there will be this final value for this will be P over 1994. And then we'll jump to the next year and we will know that P over 1994, times 1, plus G2 will transform into P 1995 and so on. But okay, if we want to reproduce this process, we need to add this growth rate that existed in the past. What is not so problematic, we can collect it from different statistical offices that take time to dedicate the work to produce all these estimates, and they can provide it. But what we're being asked is the average annual rate of increase. So now, instead of keeping adding all this, we'll just say, okay, this G will not be the specific data for the year, but will be an average value, a general one. So on average, we can now say, okay, P of year T times 1 plus G, that is the average, will produce P of year T plus 1. And if we keep on recurring this, we will obtain as a final output for jumping from 1993 to 2005, we'll get this result. P0 times the product from T equal 1 to 12 of 1 plus G. And as G is constant for all these cases, we'll get this known formula. Okay. Up to 12. Okay, so we know all this. Now we also have the data. We know that this will be, equal to P 2005. P n. Let's call n the final period. Okay. Okay. So now we can just operate this expression. I will say, okay, 107 initial price times 1 plus G up to 12 will be equal to 2.31. Okay, and from this we can solve for G. For this purpose, we will call maxima. I will open maxima here at the end. I will open maxima. I will load ngCom for just in case it is necessary. Okay. Okay. And then I will open maxima here to do all the analytics. Okay, so 2.31 divided by 107 up to 1/12 minus 1, okay, will produce the final output. And from this, we can get J equal to 6.62. Sorry. Okay. So that's the final result. Okay. We'll repeat this process plenty of times. This is the typical mathematical arithmetic approach to obtain an average growth rate. Okay. So this expression, this averaging, will be commonly used and will be in the background of all our theoretical developments. Okay. Because the hypothesis of having a constant growth rate will be quite common. To average data, we have to adjust. Let's see the second exercise. We have here a deposit. It's quite similar to the previous, but which we will make some minor adjustment, but we will use the same logic. We have a 500, let's assume it is dollars. Sorry. Deposit. We have seen a contract with a financial entity. We deposit now $500 and we will have 598 in 3 years. Where are they paying us? Okay, we can repeat the process, the previously developed process. Okay, the initial payment, let's say it Q0, will be transformed after a year because we are dealing with a compounding, okay, analysis as a reference. We will always use the annual compounding as a reference. 1 plus R or 1 plus I, the interest. This will be transformed into Q1. Oh, sorry. Perfect. Then we can also say that Q1 kept during another year in the bank will be transformed into Q2. Sorry, once again. And finally, we know that Q2, if kept in the account during another year, will be transformed into this. That will be final Q3. So we have here three equations. We know Q0, Q1, we know Q3, and we want to know how much, hmm, how long does it take? 3 years. How much, how high rate of interest we need in order to guarantee that we transform these two amounts. Okay, the problem is exactly the same as the previous. We use the compounding and the exponential function, and the problem is reduced again to this that you're already familiar with it. Q1, if compounded 3 times at a constant rate of interest, again, we can discuss what happens if the rate of interest is not the same all of them in every year, will be transformed into this. Okay, but again, we know Q1 and Q3, so obtaining the interest that matches these initial and final points is quite simple. Okay, if we take our frac Q3, okay, over Q1, okay, anyway, introduce an exponent of 1/3 to this, okay, minus 1 will be equal to the interest. And this interest is the average one that matches all these trajectories. There may be plenty of trajectories that match this, just if we use a different interest per year. But we're assuming that there is only one constant interest rate in all the periods. So again, we can now, once we have solved the problem, call maxima and say, oh yes, please, can you tell us? Sure, what are the values? 598 over 500 up to open brackets root open brackets 1 over 3 minus 1 will give us the rate of interest that solves the problem. Unfortunately, we don't want the exact value, but just the numerical approach. So as for it, oh, that's beautiful. In our case, I will just copy this. Yeah, it's not so nice. Now frac up. Okay. Oh, something's wrong here. minus 1, okay, equal to 0.06 or 6.1%. Okay, so we have solved the same problem, okay, but with different data. These are prices growing with a constant growth rate per year, and these are amounts of money growing with a constant growth rate that is connected with it. It's actually the rate of interest. Okay, so no problem for that. Okay, so now we can transform an initial amount of money into a final amount of money, provided that we know the rate of interest that is moving, is pushing the value up. Okay. Okay. Let's have a look at the next one. What we have here is a set of cash flows. One of them is a known, it's an initial positive investment, possibly, and then different withdrawal, different payments we collect from the. It can be considered either that you deposit an amount and you receive back some payments, or that you receive a loan and you have to pay back into to different moments. But in any case, we have to balance this set of cash flows. The purpose of this is to establish and clarify that there is always this balance equation that is always with us. Let me just first create the growth rate. Okay, we have, let's reduce this. Okay, introduce the arrow. Then this is, okay, this is the temporal axis. We start with an unknown payment. Let's see a deposit of P. Okay, we don't know. We still don't know what P is, how much is it, and we know that we have to wait 3 periods and pay. Don't pay too much attention to the differences there from the same. Just need to know that this is positive, this is the opposite. This can be negative, and then those will be positive. But they have different things because they represent this different cash flow. In one case, you pay or you receive, and then in the other, you receive or you pay, depending on which one you choose. Okay. So we have this app. Let's call this 400, and then let's call this. So we have 400 here and 600. And we know that the rate of interest is I is equal to 12%, if I'm not wrong. Okay, perfect. So let's crop the sign in order to save a space. Okay. And we're going to balance this. And this will be the standard case in finances. We always have to balance two components of it. What is the present equivalent? Okay, at the end, give me an initial value that balances this set of cash flows. Give me an annuity, give me different values that are equivalent. Actually, we are trying to build an equivalent expression. We'll see this later. So let's see. On one side, we have P, and P, as far as it is present, we can directly use. Okay. So left side or downside of the arrow graphics is P, and P has to be equal to upside of it. Okay, and this will be 400 on one hand plus 600, but this is not valid. Oh, be careful. This is false. This is false because having this, let's say 1,000 amount here, will give you the opportunity of keeping this money in the bank and obtaining an extra profit. So they are not equivalent. Okay, so this equation is false. We have to balance according with the opportunities the financial market creates. Okay, we have learned in the previous exercise that the interest push up the value of a given amount towards the future. Okay, So we could actually take this amount here or push this forward. That could also be we'll do both. So we are going to use as a basic reference t equals 0. Okay, so we are going to correct this expression in order to make it acceptable from the financial point of view. And we'll say, okay, the present value of P is known. And what is the present value of this payment of 400 being done at T equal 3? Okay, this amount we will obtain previously, this amount that we will call present worth of 3 with a rate of interest of 12%, oh, sorry, at T equal 3. Okay, sorry, it's 400, not 3. We'll need to take into account these three factors. First, the amount of money, then the rate of interest to be paid, and then the number of periods that presumably this equivalent amount could stay producing 12% in the bank. So let's call this Q1. We still don't know which is it. Q1. I will say, okay, what do I know from Q1? Well, we obtained in the previous exercise. Q1, if kept in the bank during 3 periods, let's say directly expression to avoid the fraction, during 3 periods, will be transformed into 400 as we did before. The only difference is that now we know the rate of interest and we don't know the initial value, and from this we can obtain the present worth of this. Okay, how do we get it? Q1 is equal to our frac, sorry, 400 divided by 1.12 up to 3. And this can be calculated easily. Okay, I will introduce here another trick. So this amount is the amount that if we deposit in the bank at 12% during 3 years will produce this 406 in 6 periods. Using the same logic, okay, we will reproduce the process for both payments. So 400 plus, I will just copy and say, okay, this is 600, and 600 had to be deposited 5 at T equal 5. Okay. Okay. And then we can, using the same for executable maxima, okay, 400 over 1.12 up to 3 plus 600 over 1.12 up to 5. And this amount is the amount that we should put in the bank at 12% during 3 and 5 years. Okay, let's go back to the script. It's okay. So this is the amount that if invested at this moment will reproduce the payments. Okay. Then if the upper part of the graphic has to be compensated or balanced by the lower part of the graphic, then P has to be this amount. Just to confirm, let's see what happens if we keep the money, this amount. We will copy this amount, okay, and I will now open Maxima directly here. Okay, we invest this, we keep it during 3 years, okay, so we will obtain this amount, we keep it in the bank during 3 years, we will get this amount. It's quite a lot of money, much more than required for the initial payment. Then we will extract from this 400 and we will make the payment. Then we have 478. Okay, so what happens if we keep this 478 in the bank during an additional 2 years? Okay, 1 and 2. We'll get the 600 initially. So it is true, we have demonstrated that with this amount of money, we can reproduce this cash flow that had been established. So the equivalence has been proved. Okay. Okay. So let's enter into the next exercise. Today, Julie borrowed $5,000 to purchase furniture for her new house. She can repay the loan with two different possibilities. Okay, let's check what happens with each one of them. Okay, we have this amount. We have to pay 5,000 in 5 payments with a given rate of interest. Okay, let's draw the graphic as always, just to clarify what we are doing. Okay, I will move this to the left so that I have space. And one alternative, as far as we have to pay back this 5,000, that is the money we receive, we're not gonna pay too much attention to this. We will just check, okay? We will just check if which one of the proposals to paying back is cheaper. Okay, so we have an amount that reimburses this. Oh, sorry. Okay, this is temporal axis. We have 5,000 here. Let's say this is 5,000. And then we have 5 amounts. Oh, okay. An annuity. We don't know how much is it. Okay, we have these 5 payments, and these 5 payments have been calculated so that they reimburse the money with a 5% rate of interest. Okay, and this is 5,000. Okay, so we're just repeating the process. Okay, I will crop this to make it smaller. Okay, and we will just obtain this Q. So this Q is repeated 5 times. Let's see how we compute for this. the present worth of an annuity of value Q I will put this just to differentiate from the previous function. Present worth of an annuity. We will organize this later on. We'll give names to this, a specific name to this expression, just to note that it's a different function from the previous one. Okay. We have an annuity of Q. The rate of interest is 5%. Okay. And there are 5 years. Okay. How can we compute this? Well, just as previous. This will be fraction Q over 1/5 for the first one, plus Q over 1/5 for the second, plus Q over 1/5 for the third. And we will repeat this until the end. Let's copy and paste. Okay, plus, oh, sorry, plus 4 plus 5. So just repeating this, and we can do it easily because Q is a constant value for all of them. Okay, but there, let's see how can we handle that. If we look, this is a sequence of values, and each one is different from the previous just by multiplying by 1/105. So this is a geometric progression. How can we obtain the sum of the 5 terms of this geometric progression? Okay, we should remember that this amount, okay, could be, okay, let's obtain totally. Okay, I will just copy this, and I will multiply all the series by this expression, so frac 1 over 1 plus r. Okay, so 1/5 in our case. Okay. Okay, then we just multiply all this expression. So I will just get rid of this because everything has to be enlarged. This one will be a square, this cube, and this one will be up to 6. Okay. Then let's do something that is quite simple. Let's subtract all this expression. Okay. Then this will be okay. I'm subtracting this. Okay, it's operating, and then I'm cancelling all the terms that are repeated. This minus this. Okay, one. Yes, let's put a minus to all this. Okay, and just add these two expressions will give us this, and then I will cancel this term with this term, this one with this one, this one with this one, this one with this one, and then the result will just be, copy this, will be as simple as this, minus, and this will be 6. I will call this 5 plus 1. The 5 in initial cases plus the 1 that we have added by multiplying by this. Okay. Then we can obtain from this the present worth. Okay. To abstract. I'm using LaTeX accounting. Okay. Divide by this. That is also easier to handle. Okay. So I will operate here. Very easily. This will be transformed into 1 of 5 minus 1. Okay. Okay. I will get rid of this. Just to simplify, it's easier to. Okay. Okay. Then we can easily simplify this. We can get the out. We can first multiply by q times. This will be 1 minus this one has to be eliminated. Okay, and this has been taken out, so this is 1. And here what we have will be 0.05. Okay, because this one will be eliminated. We cancel with the upper ones. So this is cancelled with this. Okay. So this is the final expression that can be typically seen as this. Is the conventional form. Okay. So with this expression, we will obtain the present worth of this. So it's quite easy to get. We will say yes, that 5,000 will be equal to q times this expression. I will copy it directly and check if, okay, it's okay. There are extra brackets, but in any case, everything is okay. Sorry. There is a missing multiplier there. Oh, this one is extra. Switch. Okay. So let's check it this time. Okay. So we have this expression. Just solving for q. will give us, oh, and for numeric, okay, Q is equal to 1154, okay? Y 154. So now we know this Q. But there is a different alternative we have to consider. Let's move here. Sorry, let's open. Just to enlarge the space. Okay. Let's get out of the crop for a moment and keep on doing this. Okay, so we'll better move it here, possibly. And we have a different possibility of payments. That is one single payment in 3 years' time from now, okay, with an interest based on 7% rate of interest. So one single Q obtained here then this will be equivalent to 5,000. Okay, so how much money will we pay in 3 years' time if we charge 7% rate of interest? Okay, now we will repeat the process, but not so long. Okay, I will say, okay, present worth we will want to obtain the present equivalent that, if invested, will reproduce this payment, okay, at 7%. Okay, so if we introduce 5,000, of Q, 3%, no, sorry, 7%, 3 years. And this equivalent should pay back, okay, should pay back again the 5,000 because we have to reimburse the payment. Okay, then this is easier to handle. We can do it here. We already know that Q, sorry, that the 5,000 now multiply by 107, oh, 07 during 3 years, this case, will be transformed in this amount. So with 6,125 something, we'll pay back. Okay. So now we have been able to reproduce all the proposals in terms of obtaining the present value, that is 5,000, and transforming it into the proposal made. Okay, let me close the graphic. cropping it. Okay. And this is the result. Obviously, if we want to compare those, we will have to check what is the actual rate of interest in the market. And then we don't need to do so much mathematics. If the bank is providing us with credit at 6%, this payment is very cheap, and this one is very expensive. This is below market condition. This is above market condition because market conditions are 6. Okay, so we'll stop here and we will start again later on.